Okay, so the next thing we need to learn about is resistance. Now, we learned about resistance before. We know that resistance is a measure of how difficult it is for the current to flow through somewhere. So we can think about the resistance as equal to the amount of voltage needed um, to cause a certain current. So the voltage per current, okay? Remember, the voltage is the amount of energy per charge. So if you give something enough energy, how much energy would you have to give the charge to get to a certain current? So you can calculate it by the voltage divided by the current. So let's we we can look at the total current here. The total current was equal to um, 1.8 amps, and the total voltage was equal to 9 volts. And if we compare that with over here, we've got I'll just write it in black. Actually, it's already in black. Okay, so I total is equal to 0.45 amps, and V total is equal to 9 volts again. So hopefully you'll be able to see straight away which one has the highest resistance and which one has the lowest resistance. So let's see if you can work out what is the total resistance on the parallel circuit and what is the total resistance in the series circuit. So good, the resistance is voltage per current, so voltage divided by current. So 9 volts divided by 1.8 is 5. The unit for resistance is this Greek letter omega, and the way you pronounce that's the unit symbol. The unit is called an ohm. So ohm. But the letter that we're using as a symbol is the Greek letter omega. So so weirdly enough, the total resistance is a lot less. Well, it's not that surprising, I suppose, because you can see it'd be easier for the electrons to go through just one light bulb each as opposed to two. But it's surprising that it's not just twice as easy, but it's actually 4 times as easy to do that. So I wonder why that might be. Well, let's imagine that we had to. In fact, I've got quite a good animation to explain why going through two in parallel is 4 times as easy as going through two in series. Let's just have a look at that. So this is a really good animation because it demonstrates, it creates a nice analogy for a resistor. We've got these cars. These are like the electrons in the circuit. They're trying to go along the road, but they have to go through this ticket booth. And just like a circuit, just like a resistor, the ticket booth slows down the flow of the cars. And of course, if we had two of them in series, it's going to slow them down even more because now they have to not only go through one, but they have to go through two. And that is why in series circuit, in a series circuit, you can actually say that the total resistance is actually equal to one plus the other. So in a series circuit, V total is equal to R1 plus R2. That's in series circuit. Okay, it slows them down even more because they have to do twice as much. Now, let's go down. What we want to know is, if we could actually get a timer maybe here and just count 1, 2, 3, 4, and see how many we can go. Let's compare this to the circuit. That's what it would look like as a circuit. Okay, so this is the analogy. Let's reduce it down. There's two. That's another symbol for a resistor, by the way. That's another way you can draw a symbol for a resistor. Now let's look at them in parallel. Now when we see, even though it's got two resistors, it's actually going to increase the flow of the traffic, isn't it? Because now more can go through at the same time. And so clearly the total resistance is actually less. If we imagine the resistors are just as difficult to get through, then I would say that two resistors in parallel are actually going to make things twice as easy. And it makes it a lot easier if we go back down to just we won't but so it makes it a lot more obvious if you add loads in parallel. So there's